Section 1.5 is called Vectors in Motion, and this is where we're going to start using a diagrammatical representation to talk about quantities that have a direction and a magnitude. Magnitude is a word that means just how big, putting a size to something, like a number can represent the magnitude of something. First some definitions here. We have vector and scalar. A vector is a quantity that needs to be described with the size and direction. So if something has a magnitude and a direction associated with it, it is a vector. A scalar just has a magnitude. It can be described by size alone. Of the things that we have talked about so far, some of them are scalars and some of them are indeed vectors. Some of them have directions. Time is a scalar. Time only has a number associated with it. You never say 15 minutes north or upward. Unless I suppose someone could be driving, you could tell them directions as 15 minutes north, saying you're going to drive about that much time north. But that quantity together isn't actually a thing. They're two separate things. Distance is a scalar. It's just a number that tells you how far you've traveled. Average speed just tells you how fast you've been traveling. These are only numbers that tell you a magnitude, how big something is. Vectors include directional stuff. Position is a vector. Where you're located in reference to an origin isn't just a number. If I said something is 5 meters away from me, there's an infinite number of spots 5 meters away from me. If I'm at this location and there's a can of soup 5 meters away from me, technically all the points 5 meters away from me form a circle. There's only one specific point 5 meters away from me where this can of soup is located. Soup. I could use an arrow to represent where that location is in reference to some origin. Displacement, which is the change in position, is also a vector. It talks about your change in position and how far you've traveled and what direction you are from where you started. Average velocity, also a vector, having a direction associated with it. So we're going to use an arrow to represent a vector. A vector quantity, whether it's position, displacement, average velocity, or any vector quantity, can be represented with an arrow. This is a picture to represent it. And the way that we represent the magnitude is by looking at how long the arrow is. A longer arrow represents a greater magnitude, a greater size. The way that we represent the direction is by looking at which way the arrow points. So the direction of the quantity is represented by the way this arrow points. So if I wanted to represent a position, maybe this is representing 10 meters to the northeast. If we think about a compass direction, north is generally up and east is generally to the right. So this could be a 10 meter to the northeast position. If I wanted to represent 5 meters to the northeast, what I could do is I could say, I'm going to point my arrow in the exact same direction. Let me clone this arrow really quick. But instead of being this long, I'll make it half as long. So by shortening the arrow by half, I'm representing a position that's only 5 meters away, but in the same direction. And again, if this represented a displacement, it could be a displacement of 10 meters. This could be a displacement of 5 meters. This could be showing an average velocity of 10 meters per second. If I wanted to show an average velocity of 5 meters per second in the same direction, I could just make an arrow that's half as long, but pointing in the same direction. And if I wanted to show 5 meters to the northwest, I could just point it in a different direction. I can point it wherever I want it to point. The length will tell you the magnitude. Which way it points is showing the direction. So in the next slide, I'm going to show you a way to add together vector quantities, because they add together differently than numbers add up. Typically, numbers add up just, 5 plus 5 is 10 kind of way, but a vector 5 units long plus another vector 5 units long does not necessarily give you 10. So the method that we add vectors together with is called the tip-to-tail method. And for now, we're just going to make a picture. If I want to add these three arrows together, and they could represent something. Maybe they represent three different displacements. Someone maybe walked this far northeast, then this far south, and then this far towards the northwest. To find the total displacement, to add together these three vectors, I could apply this tip-to-tail method, which goes like this. You take all three of your vectors and you redraw them so that the tip of each vector is connected to the tail of another vector. This part of the vector over here is called the tip, and this part of the vector is called the tail. So I'm going to connect all three vectors so tips and tails are connected. Basically making a chain. I'm making a chain of vectors where all the tips and the tails are connected. And once I've done that, in this case you'll notice the chain doesn't connect. The sum of these three vectors is a vector that completes the chain, but points from the beginning of the chain, which I'll make here in purple. This is where the chain begins. This is where the chain ends. So this arrow from the beginning of the chain to the end, it's called the resultant. The resultant is what we call the sum of vectors. And when you add together scalars, or just numbers, you get a sum. But if you add together vectors, you get a resultant. It's just a name. You'll notice some interesting properties. First off, if you start here, and if you walk northeast this much, and then south this much, and then northwest this much, you end up here. The red arrow is showing you where you are in relation to where you started, which is your change in position. So it makes a lot of sense, if these vectors were all different displacements, that the red arrow would be your total displacement. The order of operations doesn't matter. If I start with this one, and then this one, and then this one, I'll get the same thing if I switch it up. So if I start with this arrow, I'll put it over here, and then I add to it this arrow by connecting its tail to the previous one's tip. And then I add to it this arrow by connecting its tail to the previous one's tip. The resultant vector, which is this red one, is still the sum of these three arrows. It didn't matter which one I added in first. Put it on there. So you see, it still completes the chain. It doesn't complete the chain in that it goes back to where we started from. Again, the resultant is drawn so that it goes from the beginning of the chain to the end of the chain. Notice how it's pointing this way. And that's how you could add 8 arrows together and use this same method, or 2 arrows. There's some practical reasons to do this. Again, if we take a look at, say, a walk to the east and a walk to the north, if you started here and then you ended here, your total displacement could be represented by this green arrow. And this green arrow is the sum, or resultant, I should say, of these 2 individual displacements. A displacement to the east plus a displacement to the north is a northeast total displacement. We could put numbers on these. If it just so happens that you're adding together 2 displacements that form a right triangle, then I could use the Pythagorean theorem to find out how long the resultant is. I could say that a squared plus b squared is equal to c squared, so that my total displacement would be 9.0 meters squared plus 16.0 meters squared equals my total displacement squared. So I need to take the square root of all of this. If I grab the calculator, Like the total displacement should be 18.36 meters, which is probably too many sig figs. This has 2 sig figs, this has 3. I'm performing a squaring operation here. I'll leave it to 1 decimal point, 18.4 meters. I could also find out this angle here, by the way. This angle would tell me which direction this vector is pointing. Now, it's pointing northeast, but there's a lot of different northeasts here. I mean, if it's pointing this way, it's also northeast. If it's pointing this way, it's also northeast. We could use an angle to tell specifically how far from the east it's pointing. One of the ways we could do that is we could use an inverse tangent function. We could say, since we know the adjacent side and the opposite side, we could say the tangent of that angle theta here is equal to 9.0 over 16.0, because tangent is opposite over adjacent. So if I work out that math, well, I suppose first off, 9 divided by 16 is 0.56. 0.5625, so 0.563. To get theta by itself, I need to take the inverse tangent of both sides. The inverse function of tangent will undo tangent theta. On the left side, I'll just have theta. On the right side, I'll have inverse tan of 0.563. So I'll get theta is equal to, make sure you're in degree mode, which I was not in. Theta is equal to 29.37 degrees, so 29.4 degrees is fine. And the way that we would say this is that this displacement, the total displacement, is equal to 18.4 meters and 29.4 degrees north of east. If this way is east and this way is north, then this vector is north of east by 29.4 degrees. So here's a vector that is 45.0 meters. So maybe it's representing a position. Maybe it's representing a displacement. Since I'm changing position, let's say that this represents some displacement. I'll say delta x is 45.0 meters. And sometimes we use this angle sign to show the angle at 33 degrees north of west this time. So we're going north of the westerly direction, so this is a 33-degree angle. Could we use this information to find out how far north, so just this vector here, how far north are we from where we started? And then how far west are we from where we started? That's this vector over here. We'll see later on in the course that these are called components. They tell you, or they break down a vector into just its horizontal and vertical parts. This horizontal part tells me how much west. This vertical part is telling me how much north. And I could use right triangle trig for this. Remember that sine theta is opposite over hypotenuse. The opposite side is the north side. So I could say that the sine of 33 degrees is equal to this opposite side divided by 45 meters. So the opposite side is going to be 45 times the sine of 33 degrees, and 45 times sine 33 is 24 37.5 meters. And likewise, keeping in mind that cosine of theta is adjacent over hypotenuse, the cosine of this angle, 33 degrees, is equal to the adjacent side over 45 meters, the adjacent side representing how far west I've traveled. So the adjacent side would be equal to 45 cosine 33 degrees. The adjacent side is equal to 37.7 meters. So what these are telling me are that if I happen to travel from here to here, this is 45 meters, and I've walked 45 meters from here to here at a direction of 33 degrees north of west. This is the exact same thing in terms of displacement as if I walked 37.7 meters to the west and then 24.5 meters to the north. If I walked 37.7 meters to the west and then 24.5 meters north, I will also end up here. The same thing as 45 meters at 33 degrees north of west. And one last thing that I can do with vectors, I could add them to my motion diagrams now. I'm going to use vectors to represent the idea of average velocity between each one of the time intervals. I can take a marker here, and I'll make them in, no, I'll make them in red ice. Well, I'll make them in blue. And to each one of the dots, again, the dots are representing the position of a particle at different times. I could attach a vector that represents the average velocity as time goes on. So the average velocity between time 0 and 1 could be represented by an arrow like this. Between time 1 and 2, something like this. Between times 2 and 3, something like this. Between 3 and 4, something like this. And between times 4 and 5, something like this. So as time is going on, and again, this could be a lot straighter, the average velocity is increasing. And we see that by the spacing of the dots, but we're also seeing it with the arrows. Over here, I can see that the object is traveling at roughly a constant velocity and moving to the left. Between times 3 and 4, the average velocity is 0. It hasn't moved right or left. And then when it starts moving again to the right, it's moving slower because it's changing its position less every second than it was before. So these arrows can be used to represent the average velocity between instances of time. So you'll start to see motion diagrams in the book and then in these lectures as well, where we've attached velocity arrows, velocity vectors, onto our motion diagrams, onto the particles.